Hi, this is Savitha, Assistant Professor, Department of IT. In this presentation, we are going to see how to efficiently use the bandwidth of the media using the concept called multiplexing. So, the bandwidth of the media will be usually higher than the bandwidth of the system. So, to combine the signals of multiple signals over the single data link, we can use multiplexing. Multiplexing is a set of techniques that allows the simultaneous transmission of multiple signals across a single data link. Whenever the bandwidth of the medium linking the two devices is greater than the bandwidth needs of the devices, the link can be shared. It comprises of two devices, the multiplexer and another one is demultiplexer. Multiplexer, it combines a stream of signals from the input devices. In the opposite side, demultiplexer, it separates the streams and direct into intended receiving devices. So here is the structure of a multiplexing concept. Here one side we have multiplexer, on the other side we have a demultiplexer. The need of the use of the multiplexer is to combine the signals from the input lines. And another opposite side demultiplexer, it filters the combined signals into multiple signals which is being sent to the destination systems. So it is an analog process and it is a combination of analog or the digital process. Here the path refers to the physical link, whereas the channel refers to the portion of the path that carries the signals. There are three categories of multiplexing. One is frequency division multiplexing, wave division multiplexing and time division multiplexing. Here the frequency division and wave division multiplexing or analog signal transmission, while time division multiplexing is digital one. Frequency division multiplexing. It is an analog multiplexing technique that combines analog signals which can be applied when the bandwidth of the link is greater than the combined bandwidth of the signals to be transmitted. Here in multiplexing, the signals are modulated onto different modulated carrier frequencies and combined into a single composite signal. While demultiplexing, it uses a series of filters to decompose the multiplexed signals into its component signals. Channels must be separated by stripes of unused bandwidths called guard bands to prevent the signals from overlapping. Here we can see the process of the FDM where multiple input lines. Here we can see the telephone lines where the analog signals from these telephones are combined using this FDM process. Before combining the signals are modulated using a modulator. It is modulated onto a carrier frequencies. The signals from each devices, here we can see different signals, and these signals are modulated onto carrier frequencies. The modulated carrier frequency signals are then combined into a single signal. So next is wave division multiplexing. It is designed to use the high rate data capability of fiber optic cable. The optical fiber data rate is higher than the data rate of the metallic transmission cable. Using the fiber optic cable for a single line weighs the entire available bandwidth. So multiplexing allows us to combine several lines into one. Here the multiplexing is similar to a prism wherein which the input signals are combined and then using another prism for demultiplexing the input combined the signals. The next one is time division multiplexing. It is a digital multiplexing technique for combining several low rate channels into one high rate one. Here there are two types of FDM. One is the synchronous FDM and another one is an asynchronous time division multiplexing. Here in synchronous multiplexing time division multiplexing, we have different frames. The frames will each frame. So we have the number of frames. Each frame will contain a time slot, the time slot will be equal to the number of input lines. So here we have 4 input lines. So in each frame we will be having 4 time slots. Each time slot will be allotted for single input lines. So the data from this first input line will be placed onto the first time slot. The data from the second system will be placed on the second time slot. Similarly, all the input lines will be placed into the particular time slots allotted for that particular device. Here the multiplexer allocates exactly the same time slot to each device at all the times. So time slot order does not vary from frame to frame. Addressing is not needed as the order of the receipt tells the demultiplexer where to direct the frames. Time slots are pre-assigned and fixed. If the sending device is not transmitting, the slots will be empty and much of the path will be empty. So it is one of the disadvantage of synchronous time division multiplexing, where in which the input lines, if it doesn't have any data to be transmitted, the time slot will be empty. We have to include a framing bit between each time slot within each frames here. So for what is the need of having this frame bit is that one or more synchronizations are needed to be added at the beginning of each frames to overcome during the time inconsistency. It is not sure that the order of the frames will reach the destination at the same order as it was being sent. So if the order of the frames is it is not in an order, we do not want framing bits to arrange the frames at the destination. So here we can see the synchronization pattern of the framing bit. It will be like 1 0 1. So this is the order of the synchronization bits. So at the ending destination, if it reaches the destination, the framing bits will be arranged so that it reaches in order. In the other's end, the asynchronous time division multiplexing, if there are n input lines, the frame contains not more than m slots with m less than the number of n. So here in this example, we have 5 input lines, but the time slots in each frames is only 3. So rather than being predefined, each slot is available to any of the attached input lines that has data to be sent. In the absence of the fixed positional relationships, each time slot must carry an address telling the demultiplexer how to direct the data.